Okay, so good afternoon, everybody. This is your Chairman Saki. And this afternoon we have quite some constant. Also, although almost none of us can pronounce his name, I think all of us know his beautiful words. So the floor is yours.
It's a great pleasure to be here, and I always enjoy very much being in Japan. As we'll see, this talk is very much inspired by work that has been done by people, especially here in Tokyo. What you will see is that names that will kind of come up many times. It's like Saki, also Shikano, Professor Shikano, Professor. Well, that's maybe names that we'll see, and I always enjoy very much coming to Japan. From my point of view, Japanese physics is extremely original. So people here, they have a completely different view on life. It's very much compatible with the way I like to understand and see physics. So the talk I will give today is actually the title was Entanglement with the density matrix normalization group in the generalized Landau paradigm. But then I realized actually this is about non-equilibrium or about dynamics in equilibrium physics. So I actually just the document to talk about what other things as a motivation then for coming to this process in many body physics, because I think so I'm very excited about this result, but it's not about, but it's, as you will see, it's very much inspired by my questions. What dynamics and what entanglement. So what we have recently been doing is trying to understand a little the structure of entanglement in many body systems. If you have like a many body wave function, it's well done. The entanglement spectrum on the edge physics reveals lots of information about the phase of matter. But it was always a bit of a mystery what exactly these generalists in this entanglement spectrum, where they come from, how can you deal with them, what is the origin of this? And it turns out that actually the origin of this has to do with dualities. That is something that is very much part of this new way of looking at many body physics in the generalized Landau paradigm. Anyway, let's start with the dynamic part. So what about chiral fermions on the lattice? Okay, so as you will see, this will connect smoothly somehow to the rest of the topic. So I think this is, as far as I learned in recent years, this is one of the grand challenges in the field of quantum simulation, how to kind of deal with interacting chiral fermions. Of course, this is not a new problem at all. People have been aware of this treatment for 50 years, and it's one of the central problems in lattice QCD. Actually, my colleague in Cambridge, David Talk, he gives very popular and very nice talks about this, and the title of his talk was "Do we live in the matrix? Is it actually possible to simulate nature, namely the continuous field theories, on somehow by putting this on a computer, by discretizing this, by actually simulating this on the lattice?" And so there is an obstruction to this, and this is this very famous Nielsen-Binomiya theorem that tells that any local Hamiltonian fermions on the lattice with a local conserved U1 charge must have basically the equal number of left and right-handed fermions. And if you can restrict yourself to a one-dimensional Hamiltonian body system, it means that if you want to simulate a chiral fermion, if you have left movers, you will automatically also have the same one. So there's kind of obstruction to do this with local Hamiltonians. And this is, of course, a big problem if you want to simulate the standard model of a quantum computer, because a quantum computer will also discretize this. You have to kind of try to solve this. So recently we were interested in this problem, but let's kind of try to see what the issue is. So if you discretize a derivative in the usual way, well, you just say, okay, we can take some kind of derivative, and then if you want to simulate something like a chiral fermion like this is like a part of this while this is somehow part of the equation. If you get a wild version of it, this is a chiral fermion, and you put this on the lattice, you discretize this, you get h times twice. This is of course a free fermion. This is just a one. You diagonalize this, and what you see is that actually well, the dispersion relation for small matter is perfectly okay. This is linear as you expect, but of course, if the dispersion relation goes up, it has to go down because this is a continuous curve. It has to kind of be like with respect to 2 pi. So if you have something that goes up, that's the point it has to go down. And these mode here, this unwanted left move, this is just the right move, will of course be very annoying if you start adding interactions. If you start adding interactions, somehow this will automatically couple these very low energy modes, and the physics that you simulate is actually not the one that you want to see. So if you look Wikipedia, that's what I did just yesterday evening when I prepared this talk. I just wanted to see, okay, what is people, of course, this is a very, very famous and old problem. And of course, the lattice theory community they have come up with many, many solutions, especially in the 70s, 80s, 90s. And if you look at this whole list, all of these solutions have kind of some chiral symmetry. So these domain formulas are actually, I think, the most famous, the most popular ones to deal with this problem. It's by embedding basically your chiral theory as the edge of a higher dimensional theory. Okay, which is, of course, this comes at a huge cost because now you have to simulate this higher dimensional theory. You have to add the dimension to your system, but there's many kind of other groups. Actually, the two kind of equations that are the two formulations that you are maybe interested in including is Dominic fermion and the Stacy fermion. This is something that has been completely ignored. So this is Stacy was a student in England and quit physics because nobody listened to what he was saying, but it's actually extremely interesting what he did, as you will kind of see. So the two proposals that are relevant are these dominant fermions. So this is mainly Kaplan group acoustis that simulate the chiral theory as an edge. So this is, of course, the natural way in which we would kind of understand chiral theories, and there were also kind of very nice talks yesterday that did this. But actually, Stacy had a completely different kind of first side, completely different kind of thing. He said, why don't we use non-orthogonal orbitals? Okay, because of course, when you discretize something, there's no reason why the orbitals that you use have to be kind of orthogonal orbitals. And actually, if you think a little bit about it, using non-orthogonal orbitals is very, very similar to using implicit versus explicit methods for discretizing a derivative. So you all know from your classes in applied physics, applied mathematics, that if you solve a differential equation, there's many different ways in which you can solve this differential equation. Mainly directly discretizing it, but you can also use somehow the information about the forward step and backwards. There's this implicit ways of solving differential equations that are actually much more sophisticated, but somehow and sometimes work much, much better. And this is actually exactly kind of what is going on here. Okay, so what is this implicit method? So basically, instead of kind of defining your fields on the lattice sides, you say, okay, let me kind of define my fields in between. Okay, this is like using the orthogonals, and then you write down your equation like delta t sine of x is minus delta x. With this new kind of equation, for example, the value of that field at that point is the average of these two, and somehow the derivative is the difference of these two. And what you see is actually that these orbitals are not internal because, of course, the value of this kind of point affects this point and this point, so they're not internal orbitals. You write down the kind of equation for somehow this Dirac kind of equation, and what you see is that actually the differential equation becomes something like this. And if you kind of look at the dispersion relation, you kind of were able to turn this sine dispersion relation into a tangent dispersion relation, which is purely Gaussian. So what you have actually done is introduced a zero mode. Okay, so basically by using this kind of thing, of course, if this field is somehow 1 and this is minus 1, 1 minus 1, so there's something like the average somehow in between, this would be completely zero. So it means that there's suddenly a zero mode in your system. And this zero mode is able to compensate for somehow somehow this, if you go back, to turn this zero into actually something to something that goes to minus infinity. So you turn the sign into a tangent by actually working with non-orthogonal orbitals. Again, this is of course purely Gaussian. So what is the somehow things that you have to do instead of solving an eigenvalue problem? Now you work somehow in a non-orthogonal Hilbert space. This is something that is well understood by people in chemistry. They work all the time with non-orthogonal orbitals like Gaussian orbitals. So this is actually solving a generalized eigenvalue. What you have to do is basically solve h times psi e times n times psi with n now a positive semi-definite matrix. And this positive semi-definite matrix actually has a zero mode. That's the one. The eigenvalues, somehow both H and N in this particular single particle physics kind of thing are circumvent both of them are recognized by the Fourier transform and so on. And so this is something that I learned about this from Professor Benaker in Leiden, because well, this is so it turns out to be very useful for simulating or understanding topological insulators. It's the only way of kind of putting continuous field theories on the lattice without breaking any symmetries. So what we did recently, actually together, mainly with associated and many other. Yes.
Yeah. Can you go back to the previous page? So the program looks non-Hermitian, but you always get real eigenvalues, right?
This Hermitian, both H and N are Hermitian.
I mean, I'm asking the eigenvalues.
But this is H and N are. So H is Hermitian, N is positive semi-definite, then you're guaranteed that all the eigenvalues are real. Not positive, just real. It is actually, this is a generalized eigenvalue problem, this is well understood.
That means you have a corresponding Hermitian Hamiltonian, right?
Yes, we play the local one.
Yeah. So you can rewrite this in 1 year basis, then you get the left hand becomes
If you want to write this, so this is a local Hamiltonian with multiple ones. So if you want, you can, that's actually an associated normal eigenvalue problem. This is how you solve it, generalized eigenvalue. But this one is very normal. Yes, so you can basically take the inverse of the square root of n, conjugate this H with it, and that's exactly how. It's very non-local. So that's and of course you don't want this if you want to simulate the one system. You want the locality is the main thing, and using this you actually keep locality while at the same time being able to deal with.
Thank you.
Okay, so what we did in a very recent paper together with Sushi Win, I think that's just graduated here. We just kind of formulated a many-body version. Okay, so basically we started putting somehow the second quantizational this, trying to kind of define creation annihilation operators, defining Hamiltonians. Somehow what is really, this was of course the breakthrough for us. So normally if you do this, it's at first sight it looks very, very hard to do something like second quantization because all these orbitals are on top. So that means that just to calculate only an overlap of two Milli-Body wave functions, you would need an enormous amount of exponentially many kind of terms to sum. But if you can do this carefully, just because of the locality structure, it turns out that actually the norm of these states in this non-orthogonal Hilbert space for the many-body version is nothing more than basically you take your kind of normal wave function and sandwich it between a matrix product operator. And for people that are familiar with tensor networks, this is like one of the most standard matrix product operator. This is a matrix product operator with Bonner-Richie force. So they're still completely local, even in the many-body case. And using this, we were able to basically solve now the full many-body problem, add interactions, and see that indeed somehow this whole kind of thing. So you have to define conjugate variables and all this. But anyway, so all the kind of things work, and Sushi can develop a completely generalized EMRG for this, and it seems that actually for this we can therefore simulate kind of in a local way, but with a twist. Of course, we are not violating Nielsen Mia because we are actually kind of circumventing it by working with generalized eigenvalue problems. Okay, but still, locality is preserved in some or the other way. And indeed, somehow this is not a very interesting movie, but if you count, this is like the real-time evolution. Because this is the only dynamics that I have in my talk. But you kind of take this Hamiltonian, put some excitation. This is already called 35 slides. You put some excitation, can involve it, and you see that indeed, basically, this excitation is moving only to the right. There's no kind of part of this of the wave function that's moving to the left. You only have moves, and indeed somehow there is still some kind of notion of locality. If somehow also the time derivative you discretize in the same way, also the time derivative you actually use this in place of necessity populated and makes an effective somehow equals to what.
What was the okay, my question was what is your interaction? So B, it looks like B is a non-local operator. So is this a local interaction? Yeah, this one.
No, it's completely local, because this is just a coupling n to n plus one. This is how.
What is P?
Oh, B is just so okay. So B is the conjugate of A.
Then it must be non-local.
Yeah, but okay, this Hamiltonian is local in the B operators.
Sure.
So, but that's somehow the way. So this is local, okay? But it's you have to define it like that. If you work with non-orthogonal orbitals, the Hamiltonian, the operators have to kind of be defined in a conjugate basis.
B has A
So it's local in B. So the B.
A has compact support, and
Yes.
B has sort of exponential decay.
Yes, okay. But the important thing is that actually the expectation value of this kind of wave function with respect to these h are all local from the point of view of matrix states. There is some this is really the local, the calculations are local. So it's very similar to just doing normal VMRG, but instead of working with this lower orbitals, you have to kind of matrix operator. So this is really the way of making everything local, which is indeed, I agree, it's not obvious to see.
What is this?
Well, this is the main spectrum. So this is like the full spectrum of that Hamiltonian on, I think, 10 sides or 11, maybe. Yeah, no. Yeah, wait, this is the filling factor. I forgot whether this is 10 sides. And this is when you fill somehow, no, this is maybe 20 sides, and you just fill the, well, actually, I forgot how many slides this is, but this is the full spectrum, and every one of these columns is a particle sector. So this is the 1 particle sector, the 2 particle sector, 3 particle sector, and so forth. Okay, so if there would be 3 fermions, then this 1 particle sector would, of course, understand. You would explain everything. Somehow the energy eigenvalues of these other things would just be linear combinations of these. But because we have fractions, this is not like this. But you see, it's still completely kind.
I think many of us are curious what this picture is. What is the picture?
Oh, this is some sushi. Who was actually, I think he just graduated from the institute next door. Yes.
Did this.
That he lives. So he really wrote this new kind of theological.
What's the boundary relation?
This is actually okay. This is a very good question because it is tricky because there's a zero mode. So actually for this we used number of particles. Oh wait, number of sides. So I think this is exactly. So it's 11 sides. That's it. There's 11 sides with periodic boundary conditions because then there's no zero modes. Okay, so if you have an even number of sides, you would have to use periodic anti-periodic conditions, but that would also be fine. It's a good question, I think. Okay, anyway, so it seems to work, and it also seems to, like during the simulation, we see that there's something like area law. So basically, the whole formalism of things that you normally do somehow seems to work. But anyway, this is just to motivate or to put it in somehow context. So what I want to say is actually that this picture, from one point of view of tensor network simulations, is actually not very different than the usual one, in which you think about kind of fermions as living on the edge of a higher dimensional theory. Okay, because so again, these pictures I will explain in more detail in the rest of the talk, and this is exactly what the topic is of the rest of the talk, is to understand entanglement structures and edge modes. But if you have a many-body wave function, okay, in the terms of a tensor network, and actually the edge modes of that tensor network are very naturally endowed with a tensor product structure. Okay, just what you say is I have a tensor network of a many-body system, and then somehow at the edges I just leave these bonds open. So for people that don't know what tensor networks, and we'll come back to this later, but you leave these bonds open and say, okay, this gives me an effective tensor network description or a tensor product description of my edge modes. And you understand, okay, let me count the edge physics, the bulk physics is gapped, and all somehow the interesting physics is going on the edge. And you're interested, okay, what is, if I can I define a Hamiltonian on this edge? And to define a Hamiltonian on this edge, you have to understand how these wave functions basically are normalized. The way these wave functions on this tensor product are normalized is basically you put somehow psi bar there. You have to kind of connect them by contracting this whole bulk, and this whole bulk is effectively nothing more than a matrix product operator. Okay, so this way of looking at generalized eigenvalue problems for doing kind of fields is actually, from the point of view of tensor networks, exactly the same as saying that this lives on the edge of a higher dimensional theory. So in that sense, it's very surprising, but somehow what is of course very nice if you do it in this way is that you don't have to get at all about this higher dimensional theory. You can immediately just reduce somehow, compactify or somehow compress all the information of the bulk in this matrix product operator that contains information that you want. And it's if you about saying, okay, let me try to understand physics, the edge physics of a many body system. Using this, you have to solve this generalist eigenvalue. And basically, this is zero modes, because this was, of course, the key in getting this function system assigned that was somehow a zero mode, this actually corresponds to the symmetries that live in the bulk theory.
So this white, so these white circles are like edge Hamiltonian, and the green contraction of green circles is
Well, this would just be normal. I didn't draw it all the Hamiltonian. This would just be somehow how do we even kind of normalize your wave function? What is the yeah, they're not orthogonal because somehow they're connected by this bulk. Somehow this thing would be this L would effectively be the right hand side of your generalized Eigen. Okay, then of course you would have some effective theory or some effective Hamiltonian also for the edge, and then this would also be in that form. But this is just a norm. This is just a norm. So this actually would be this. So maybe this is not very clear, but certainly for people like Professor Tasaki, this would be much easier for him. Of course, he knew this kind of things all along. He knew this already 30 years ago. Okay, so if you look at something like the AKLT state, which like in the 1D case, so this is effectively what you have, these singlets and these the most famous tensor network state, matrix plot state. So basically you have these singlets and then you put these projectors there. So how, and you have two edges. Okay, this is now the so-called the zero-dimensional version of this, and you want this in describing the physics of my edge, you basically have to take this MPS. Now we kind of wrote this as this kind of thing has the physical dimension. This is the virtual dimension for the AKLT state. This is what dimension 2. This is 3D system. And so the edge physics would exactly be somehow. How do you kind of come up with somehow these two kind of things to these two things? How do you kind of this normalization with effectively contracting this tensor network? You would put a wave function psi here, and you would understand how. Okay, and all it gets out there. Okay, so this effective normalization is exactly has to do with the. So there's another, of course, great person here from Tokyo, Professor Katsura, who kind of already understood a long time ago that there's a very general relationship between somehow the entire spectrum and the edge space spectrum of Tokyo. And that's exactly what we want to go to. So you want to use all of this to a bridge as a bridge to try to understand indeed now basically entanglement spectra and edge flows. Okay, so before we do this, actually, I want to say that actually this point of view of looking at entanglement and somehow this entanglement Hamiltonians and edge modes has kind of really has led to a completely new way of understanding the many-body problem. Okay, because it's really puts how the wave function center and effectively also how somehow the correlations are routed through the system. The entanglement gives you a new way of characterizing systems, and indeed, as we'll see, is that this is extremely important to kind of generalize somehow the framework that was originally set up by Landau to characterize phases of matter. You will kind of have to look at the entanglement properties, not just the. And somehow this is of course a very long kind of thing, but the really kind of crucial people that led to this whole development of tensor networks as this Affleck and Kennedy. So this is this very famous paper at the end of the 80s in which they developed somehow this AKLT states, and there were Franz Nutterhalle and Werner who realized that actually these AKLT states are just very special states of a much bigger class of wave function. And then effectively there was a huge breakthrough at the same time that these people wrote a paper by Steve White that was based himself on work of Wilson, in which he used these wave functions as these variational wave functions, and suddenly this was like an amazing breakthrough. So certainly the problem of simulating quantum spin chains from somehow exponential complexity kind of became somehow polynomial complexity. So this was a huge breakthrough. But it took somehow the let's say the development. This is Ignacio Siraki, Frei Vidal, with whom I collaborate a lot. The development of trying to understand basically why this worked in terms of entanglement theory to see somehow the connection between these things. Because it was not at all clear what Steve White did, how this was connected at all actually to this work. It was not whether it was also not clear at all whether somehow this was the full picture, whether somehow all these matrix processes or these tensor networks are actually kind of strong enough. The manifold of tensor networks is actually representative enough to kind of deal with any possible system. Indeed, this has now led to kind of many proofs and lots of development, and now we understand that basically the manifold of all possible ground states of gapped spin chains is well represented using matrix states. So if you want to make claims now about phases of matter in 1D, it's enough to basically look at these gap phases, it's enough to look at how these tensor networks, because they have the information. Of course, mathematicians say, okay, this is not enough, but then there's amazing other people like Professor Gatta, who kind of generalize this to the most general framework in which indeed this confirms these statements are true. Okay, so effectively what these tensor networks do is that they realize something like a dream that Feynman had kind of formulated in one of the very last talks that he gave. So Feynman was very interested in using the variational method for simulating field theories. Okay? He gave a talk that he tried very hard and always failed. Okay? That he didn't kind of get the right kind of ways of doing this, and he gives lots of reasons why this didn't work. But then he kind of starts in this talk, starts more philosophizing of how he envisions that it should be done. And I think tensor networks exactly kind of encode that program that he envisioned. So what he says that actually that instead of simulating the whole wave function, you should surround the wave, somehow the part of the wave function that represents it by some object, the region where you want to calculate things, by a surface, and describe what things are coming in across the surface. It tells us everything that's going on outside. And this is exactly, of course, he didn't, these notions like entanglement and all this didn't exist at that time, but that's his intuition is exactly describing somehow this entanglement way of describing many-body wave functions, not in terms of the full wave function, but in terms of the connections, how somehow the different parts of your wave function are connected to each other by the entanglement degrees of freedom. Simply these tensor networks, distinctive with the EQLT states, they exactly capture that idea. That's how you model the wave function by somehow the connections, not by the wave function itself. Okay, so this let me kind of now move to somehow the second part of the talk, which is trying to indeed somehow make stronger these ideas of what this entanglement is, and trying to explain basically somehow the entanglement structure of these wave functions, especially in 1D, but somehow we can also do this in higher. So when writing somehow a very interesting paper that was somehow about these phases of matter and trying to understand this, I did some research, and it turns out that Pierre Curie already understood that somehow phases of matter are especially interesting when you break symmetries. That somehow symmetries are the key in understanding somehow many-body physics. I really always thought that this was Landau, but it seems that Pierre Curie already kind of formulated this in a very precise way. Okay, so anyway, so what is Landau made this more precise? He said, okay, how do you characterize somehow a phase diagram? You start with specifying a symmetry. Okay, for example, certainly for quantum spin chains, this could be SO3 or whatever symmetry that you're interested in. And basically all the possible gap phases are labeled by the subgroups of the characteristic. Okay, so basically all symmetries are not broken. Okay, so these are all small phases. Of course, this is by now superseded because we also know that there's topological phases, and that's exactly why we will talk about the generalized Landau later. Okay, but anyway, these phases can be detected by local orbit parameters which transform according to a direct optic symmetry. That's the typical way in which the Landau parameter is formulated. Okay, so just to give an example of this, let's take quantum spin chain on L sides, which it's a kind of a modification of this EQLT Hamiltonian. It's a 1 Hamiltonian that it contains somehow the Heisenberg term. This is just the Heisenberg spin 1 term. Then you have somehow an HI1 term, which is somehow SXXX squared. So this breaks SO3, and so these two terms break the SO3 symmetry, but somehow the remaining symmetry is just A4, and A4 is the alternating group with 4 elements. It's basically the even permutations of 4 elements. Okay, so it turns out that this is just the symmetries that are remaining there. And indeed, you can see that basically for all elements in this group, somehow all these terms commute basically with a representation of this A4 symmetry. So why do we do this? This is because somehow, turns out for this, it's very easy to come up with all the possible subgroups and all the possible projective representations as we will need. So this is a very schematic kind of way of drawing the phase diagram. So you have basically 2 parameters, J1 and J2, and you kind of vary these parameters and try to understand what the possible phases are. And what you see is that there's actually 4 different phases. There's basically the SPD phase. This is indeed the EQLT phase, the Haldane phase. Then there's basically the purely symmetric one. There's the fully symmetry broken phase, and there's basically also a T2 symmetry that it's just the remaining symmetry. So okay, these are the possible phases You have, of course, the reasoning between exhibit phase transitions. And what I want to go to in this talk is to try to understand the entanglement structure of all these different phases. Okay, so in all these different phases, there will somehow be a very particular type of structure of entanglement that you can completely understand. It turns out, and by looking at some technicalities, and this is where to the talk. Okay, but anyway, before we do this, there's a very precise way of defining now gap phase of matter. I think the really interesting, and this really kind of came up mainly due to the work of Matthew Hastings, is that now you can make very precisely what it means to have a phase of matter, because you can determine it in terms of quantum circuits. So basically, you say that two gaps homotonic with the same symmetry or in the same phase, and there's a symmetry preserving adiabatic path interpolating between them, and of course, in the gap, even when the size of the system goes infinitely large. Okay, so colloquially there exists a G-preserving low-depth quantum circuit mapping the ground state to each other, and actually you can make this kind of really rigorous by making use of somehow this so-called quasi-adiabatic evolution ideas of Hastings. So what Hastings does is he kind of wrote down in the Hamiltonian that if you evolve in this Hamiltonian, you go from one ground state exactly to the other ground state without making any mistake. It's really the evolution with respect to this Hamiltonian just allows you to kind of go from any ground state to any other ground state without error. The price of today is that this evolution with its quasi-adiabatic Hamiltonian has backward tails. It's not strictly local, it has some kind of tails, but these tails cannot decay very quick. And then somehow this came up with some work that actually we did a long time ago in 2006 with Hastings and graphene, and in the sense that we kind of came up with lots of no-go theorems for proving using somehow the tools of Lie-Brunson bounds. We were able to prove that indeed, if you kind of have two states in a different phase, that there cannot be a low-depth quantum circuit that connects them. Okay, this is again, there's a contradiction in this, and you can do this using supports. And actually what is interesting and very relevant for the rest of this talk is that actually using these similar ideas, you can basically prove that if you have a phase of matter, you have all these different phases in this phase diagram. If there's one state in a certain phase that satisfies an area law for the entanglement entropy, then all of them will satisfy for the entanglement entropy. Why is this? It's really because somehow you can connect all these phases, all these ground states to each other by a quasi-adiabatic evolution path, and then some very technical kind of results about how much entanglement can be created along such a path kind of proves that indeed somehow all these things are kind of related to each other. Okay, so if one state satisfies an area law, then all of them do it, and certainly in 1 + 1 dimensions, actually you can prove that in every phase there exists one MPS, one completely explored state, and therefore somehow all of them all the entanglement structures in a particular phase is very much related to each other. Okay, so let's actually look at the spin 1 Heisenberg model. Okay, so spin 1 Heisenberg model. So you take on a spin chain, you divide it into two pieces, kind of calculate the reduced density matrix of one part. It doesn't matter whether you take the left or the right. Take somehow the eigenvalues of this reduced density matrix and take the logs of this and plot them. Now what you see is that you have these very nice degeneracies. Okay, so you have this very nice degeneracies in the entanglement spectrum. 2-fold degeneracy, 4-fold, 2, and so forth. So this is, and actually this degeneracy structure is the same for all states in that phase. Okay, so this is actually this wave function is the one that lies right in the middle of that phase diagram that I showed you. All these wave functions in that whole phase have somehow, of course, the Schmidt coefficient themselves, the value of them varies, but somehow the degeneracy of them is actually the same. So this seems to be something universal. There's something very kind of universal, this degeneracies. And it's like first not at all clear where this comes from. Okay, so before we explain this, let's actually take a step back and then go back to Landau, kind of who said that indeed different phases of matter are described by somehow different local order parameters. And indeed, this is of course very famous Ising model in tensor magnetic field. That it's very clear that in one part you have a paramagnet and the other one you have symmetry broken, and there's an order parameter in one and not in the other. And somehow this means that this is how you typically distinguish these two phases of matter. So there's an order parameter here, there's no one. So if you subtract the symmetry, there's an order parameter. Transforms somehow, of course, under your symmetry operation. And so in the other case, there is no order parameter. But somehow the key in understanding that there's much more somehow also in these topological phases of this kind of spin 1 Heisenberg, there's something topological there, actually goes back to an amazing paper of Kalanov and Seva from 71. It's actually paper in which somehow much of the developments about about topological order and actually also conformal field theory have been kind of anticipated. So in this paper, they basically say that even somehow in the symmetric phase, you can define an order parameter. But the order parameter is local. It's actually a string order parameter. So they actually, in this paper, they kind of define a disorder operator. It's kind of a loop operator, and they show that indeed the expectation value of that operator is non-zero in the symmetric phase, and actually is kind of zero in the symmetric one. So it's kind of the opposite. And indeed, somehow the way they obtain this is by kind of doing something like a duality transformation. You go from one to the other one by somehow Kramers-Monnier duality, and indeed somehow this local, this is a very non-local expectation, right? It's just a product of many spins. But this is in the classical case, but of course the quantum case is very similar. It's kind of a string order parameter that they define. Actually at a very similar time, there was actually Franz Wegner who kind of also kind of observed something very similar. It's kind of a very, very famous paper that he wrote in 71 in which he kind of defined gauge theory. So okay, this is actually turns out to be a Z2 gauge theory in another language, in which you can set that where phase transitions that happen without having local order parameters. So indeed, this all tells you that indeed somehow there are clearly there's more to somehow the understanding phase diagrams than just the local order parameters. You also have to take into account the non-local order parameters. Okay, so these non-local order parameters, these are exactly the ones that have everything to do with the entanglement solution. Okay, these are the ones that will kind of give you these degeneracies in the entanglement spectrum. Okay, so let's kind of go back to the spin-1 model. Okay, this is the one. Somehow the current state has some topological nature, and indeed somehow it turns out that there's some kind of tangling. If you kind of have some edge modes, there's something like, well, there's so Haldane had some field theoretic kind of reasons to understand that indeed there's something topological to this. In 89, and the Mays and Ronalds, they discovered that there's indeed a very similar order parameter. This order operator is somehow the one that Elrond and Seemann defined in this spin chain. So there's something there that is interesting. And the question is now what does that mean? Okay, so where does that fit into the paradigm? And if you look at somehow the entanglement spectrum of the half chain in the spin-1 Heisenberg model, okay, so there's always kind of all these degeneracies are even. And this is actually something that is not at all. It's not easy to understand this because somehow that spin-1 Heisenberg model has an SO3 symmetry, and all the EREPs of SO3 actually have an odd dimension. Okay, so they're one-dimensional or three-dimensional, but there's no EREPs of SO3 that have an even dimension. So it's not at all clear at first where these degeneracies are coming from. But of course, when you realize that actually somehow these edge nodes, especially kind of, and this is exactly what the AGLT picture gave us, they are actually not transforming according to SO3, but according to some projective representations of SO3, which is exactly SU2, which is indeed somehow an even representation. So, and this has to be the origin, of course, of these entanglement spectrum. Okay, this is the jealousy. So indeed, in a very famous paper that Saki wrote together with Tom Kennedy in '92, is basically they really kind of made it clear that indeed there's some kind of a hidden symmetry there that is responsible for the string order. But the rest of it all kind of basically try to understand somehow this construction for more general cases, but also somehow from the point of view of entanglement theory, why this is exactly somehow the way to understand things and how it kind of will put around research to kind of a completely different way of looking at phase diagrams. But anyway, so it means that at the end, what is crucial to understand all of this is to understand the entanglement degrees of freedom in somehow matrix chloric state. So you have this NPS, and you cut it open and try to understand, okay, how does this, what happens here in somehow this interface between left and okay, so the global features of somehow the system can be kind of understood by studying the entanglement degrees of freedom, somehow the local tensor descriptions. Okay, by looking somehow at the local degrees of freedom that happen here and how they transform and what their symmetries are, you can actually deduce the global features of your system. So in that sense, it's really kind of coming back to this Landau, that is some kind of a local kind of thing that tells you what the global features are. But you cannot just look locally at some more order parameters, you really have to look at the degrees of freedom. Okay, so to make this very explicit for this one-dimensional case, there's something that is called the fundamental theorem of matrix chloric states. It tells you that if two matrix chloric states are equal to each other, this is true if and only if these tensors that describe somehow these matrix chloric states are related to each other by some conjugation with a matrix X. Okay, so it's clear that somehow if you have a matrix product state and you have one B and A that are connected like this, these two matrix product states are equal, but also the opposite is true. Somehow psi of A is equal to psi of B, then there exists such a X. This is especially interesting if you kind of have a system that is symmetric, okay, that has a certain symmetry, because it means that if I apply my global symmetry to my wave function, it has to leave the wave function invariant. Means that using this theorem that there must be somehow a V of G such that if I apply this here, there must be a V of G minus 1. Okay? And now, of course, for people that know a lot about representation theory, they will see, that means that this V of G also has to be a representation, but it doesn't have to be a linear representation. It can be a projective representation of the same thing. Somehow all these things always go in pairs. The phases don't matter because somehow there's a V of G somehow inverse there. So this can be projective representation, and that's exactly what is going on in these systems. Okay, so indeed, if you look at the AKLT model, these different tensors here, in some bases can be written down as the Pauli matrices, and if you kind of take as a symmetry a Z2 times Z2 symmetry, you can see that on the physical level, these U of G's are just diagonal matrices, plus or minus ones, and on the virtual levels, these different kind of U's, these V's that correspond to this, are just the Pauli matrices. And these Pauli matrices obviously not somehow linear representations of somehow Z2 by Z2 because there's these extra phases. And indeed, this is somehow exactly the insight that Professor Shikawa had with his collaborators, and then somehow they realized, okay, this is the way to understand somehow the fact that this is topological and so this in these wave functions. And indeed, this led to a complete classification of somehow what the symmetry protected phases in terms of somehow something called homology, second homology, or in terms of cosines of a certain. Okay, and also can include reflection, time reversal, all these kind of things. And one of the immediate consequences, of course, is the generalities of the entanglement spectrum. Because if you have a projective representation, these projective representations have to be somehow they are not reducible to one-by-one loops. They have a certain degeneracy. This means automatically the entanglement spectrum must be degenerate. Okay, so this is now kind of accepted as being somehow the full classification for phase matrix 1D. So basically, you have to kind of look if you have global on-site symmetries and you don't impose translation invariance, so you can actually vary somehow the linear path you don't have to impose somehow translation invariance. Then the full classification is basically try to find somehow a certain global symmetry of your system, your Hamiltonian, find all possible subgroups, and from the subgroups trying to find all possible ghost cycles, and this is effectively how you can characterize all these different phases of matter. Okay, so but it turns out that these global symmetries, that there's actually lots and lots of interesting quantum spin chains that don't have just these global on-site symmetries. Okay, so there's out that even for understanding, as we'll see, somehow these global on-site symmetries will turn out to be extremely useful to also kind of look at more generalized symmetries. What are these generalized symmetries? So you can actually perfectly well define wave functions, like HQEs or spin chains or whatever. You can define kind of quantum spin chains with more general symmetries. Symmetries that are not just tensor products of local operators. And typically, indeed, these are the ones that we are mostly interested in. From the first part of my talk, it's clear that I'm interested in symmetries of wave functions that live on the edge of higher dimensional systems. And this is effectively a 1D system. And indeed, somehow these wave functions, these symmetries of these bulk, especially if this is a topological field, topological phase, it turns out that this can have very interesting symmetries in the bulk. Somehow the symmetries of these wave functions somehow of the edge, of course, inherit the symmetries of the bulk, and this can be something with 3 cos cycles, it can have quantum group symmetries, and so on. Okay, so examples of this have, of course, been considered for a long time. Okay, so for example, there's this IRF Hamiltonians that Baxter introduced. Actually, you basically say is that you have some kind of rules. You have a constrained Hilbert space. So if you the Hilbert space of your wave functions is such that at every step you can kind of move up with 1 unit or move down with 1 unit, but you cannot remain constant. So this is effectively constrained Hilbert space. There's some kind of a very actually this indeed. So these kind of systems were considered by Professor Michino and Sierra. They can consider kind of wave functions There's also ionic spin chains that are, of course, that also have not, they don't have a tensor product structure, because somehow what happens, the wave function, somehow the dimension of the subspace that they span depends somehow, well, is not somehow, it's not, it doesn't scale like a local dimension to some power. There's some kind of multi-local constraints. And if you kind of look at all these models, there's many of these models that people that appear very naturally in physics and that have people studied, that these systems typically have these generalized symmetries. And the symmetries of these spin chains, they are not described by a group anymore, but rather by something that is a generalization of a group. And this is called a fusion category. Okay, so basically a fusion category is a generalization of a group. If a fusion category consists of some elements, okay, I have elements A, B, C, and so further, and if I multiply two of these elements, I just don't get a unique element like with a group, but I can get somehow a sum of elements. Can this ends or can with non-negative integers. Okay, they can be 0 or 1, and indeed somehow for this Fibonacci chain, this golden chain, for example, if I have 1 and 1 again, so 1 and 1 and tau is one tau and a tau can be a 1, but the tau and tau can be a 2. So these are the rules generalizing basically something. And indeed, somehow the first person to really take this seriously was actually Emmy Noether. Okay, so he would be famous in physics for her Noether's theorem, but actually in mathematics, she's most famous for her studies of rings. Deeply all kind of rings with additional structures. This is actually very interesting. So also this somehow this interaction around the phase models like that that I showed you on the previous slide. This is basically the rule of these kind of things. Okay, so it has to be one, then so basically the product of these two can effectively there's kind of rules of how you combine these things. And actually, so if you kind of look at recent PhD students study in my group, but in many places of the world, so people all started, especially because it turns out that these fusion categories are very relevant in context of correcting codes, but also in context of topological order. People all over the world started reading this book on tensor categories. It's a very famous book. Many people bought it. I also bought it, and I started reading it, and I didn't understand anything. It's complete abstract. But somehow, I also don't need to understand it because it turns out that the full representation theory of tensor categories can be done in terms of matrix product operators. Turns out that this is a one-to-one correspondence, and so we discovered this without with a naive way of understanding this. As physicists, we don't, I mean, let's see, most physicists don't have a good feeling, understand the representation theory much better than group theory. If you look at a Lie group, it's very complicated, but if you kind of look at the Lie group from the point of view of representations of it, it's very simple. It's exactly the same happens here with these kind of fusion categories. They are very abstract kind of objects. But if you look at this from the point of view of the representation theory, it turns out that the representations of these fusion categories are given in terms of matrix product operators. Yeah, so for a group like, say, I think a group is a special case of this. These matrix product operators would just be tensor products. Okay, the red line, there would be no index there. This would just be a tensor product of representations. But somehow what happens in these fusion categories is that there's a correlated action. Okay, how the way you transform here depends somehow on this value. The way you transform this will depend also on that value. So there's some kind of a correlated action of how you transform your things. And quantum groups, for example, are also exactly that. Yes, we can understand quantum groups also in this kind of generalized representation. We started working on this like almost, I think it's 10 years ago. We started working on this without really knowing where. That turned out to be extremely interesting. And we found that indeed for every one of these fusion categories, you can find matrix product operators that form a representation of it independent of the length. So this is something like a topological feature independent of how many tensor products you take. This somehow, this product, the sum of this NPO, the sum of NPOs with somehow integer coefficients. Yes, well.
So I want to clear. So each O corresponds to A.
Exactly. Okay, so this would maybe you should have called this A, B, and C. So this would be like NPO A, this is NPO B. This is a sum of A, B, C. This is exactly this. So indeed, the NPO is the A.
Okay. You need lots of these sites.
Well, it's independent of the size. So this should hold independent of how many sides you have.
But if you only have one site,
okay, then one might not be enough. That's okay. You need to. There's a lot of work, but from that on,
how many do you need? Like more than correlation lengths or what?
No, because there's no correlation like this. It's finite. It just depends on
Yeah.
it depends on some of the number of objects. Okay, maybe typically a few months. But it could be that you need two. We have never got. I don't think we have ever got a case where we need one.
So is this one readable? So the book is not readable, but
just linear algebra.
yeah.
Because there's just answers that you multiply with each other and that's it.
So okay.
Okay, so this is something that you can put in the computer and actually, so we learned, so this, we had an extremely fruitful collaboration with Julian Fuchs and Christoph Schweigert, who are real mathematicians who actually discovered this whole bimodule categories. They really discovered this because they wanted to understand somehow the possible modular invariant partition functions of CFTs, and they were absolutely stunned that you could actually represent them using on the computer. For them, these were very abstract things that there's no way that actually can form representations.
We don't have to buy the book, but go to this article.
You have to read my papers. No. Of course, you have to buy the book. But the book is, it's real hard math, I have to say. My students seem to understand this, but again, I don't want to. I think the attitude, the feeling that the Japanese attitude is also okay. We just do it our own way, and then we understand much better. Anyway, so together with Fuchs and Schweigert, we realized we basically found all possible ways in which you can represent this. Okay, so what you solve is basically all the possible matrix product operator ways in which you can represent such systems. And to start that for this, what you need is something that's called a bimodal. Okay, so this may be very abstract, but you will see it's very tangible if once you start expressing it in terms of tensor. So basically, this is the original category. Okay, you have an object in C, another in C, and this gives you C. This is the original category. What you need is another module, something that you can act on the left of this module with C, and this gives some. So this is basically the case of representation theory. This would be the vector space on which you act with your group. You have C would be a group, and this N would just be a vector space, and you act for doing a representation theory. You act with your group elements on a vector space. But there's that you can also act on the right with another kind of object, and this right thing is also a dual category system. And means if you kind of hard, then it turns out that the reason that all of this works is that you can define a generalization of things like Clebsch-Gordan coefficients. Okay, so this NPO here, A and B, if you multiply these two, this is equal to a sum of C, because there is something like a Clebsch-Gordan coefficient that you can pull through. If you take the tensor product of this times this, with the Clebsch-Gordan, this kind of reduces to something like this. Okay, so there's a Clebsch-Gordan coefficient in this direction. It turns out that for these bimodal categories, somehow you can also interpret this tensor as another NPO in the other direction. Okay, and it turns out that these NPOs form a representation of a different category, namely the dual category of the original one. Yeah, this is this category D, this is category C, and this is the category D, and there's also Clebsch-Gordan coefficients in this direction. Okay, these are actually, if your NPO is a group, then this red line is just one-dimensional, these blue lines are also just one-dimensional lines, these objects are just tensor products of your representations. Now this is trivial, this would be G1, G2, this is G3, there's no information here, all these things are trivial, and these objects would be the usual Clebsch-Gordan coefficients. But it turns out that you can just do this, you can do this in complete generality for all these different fusion theories.
So red is a virtual space and black is a physical space?
Yes, well, actually the physical space consists out of this triple. So that's a very natural way that emerges that your physical space are considered a triple, and it's not a tensor product structure because this index of this blue thing has to be the same, and this side has to be the same index as this. That's why we kind of throw it as somehow the same circle. So there's triples, and somehow all these constraints, like in the Fibonacci case or in this interaction interface, are encoded by basically given through by this blue line. So
can I think of this as there's always some kind of maximally entangled like bell pair?
Yes, that's another way to understand.
Enhance on top of this like.
This is the 6J symbols. Okay, but now we have this also in the other direction because you have it in both ways, both vertical and horizontal. So there's something like Bliss Gordon and 6Js, but for two dual key categories and all these kind of things go through. So it seems that actually there's a delay or something in my Zoom. But, okay. Anyway, so you come up this up, and there's all these kind of F symbols, and actually we developed. Okay, I don't know what goes here.
Okay. Share again.
Share. On the screen. This.
Yeah. Great.
Okay, now more. It's not it.
Hide video panel. We
Like floating meeting control.
flow.
No, it's not.
Go down.
High flow, yeah.
Okay.
Okay, so let's look here. Okay. So this first of all, it's so interesting when you kind of start doing representation theory is that there's always kind of this whole luggage of all kind of things that you can do with it in terms of physics. And indeed, most important application, of course, of theory is this Wigner, or certainly the most important applications that Wigner theorem. In the Wigner theorem, from somehow this point of view that is useful for us, it tells you that any observable, including points with a certain symmetry, can be written down as a linear combination of Gaussian coefficients. Okay, this is a kind of global way of understanding what Wigner tells you. If you have an observable that is symmetric, then I have to be able to write it down in terms of Gaussian coefficients. So effectively, as some symmetric operator, you have these Gaussian coefficients, and indeed, my Hamiltonian must be a linear combination of Gaussian coefficients. So think about the Heisenberg model. In the Heisenberg model, is U2 infinite. Okay, so you have basically the Gaussian coefficients that tell you how to kind of connect two signals to each other. Kind of put just your spin 1.5, spin 1.5, spin 0. This is the Heisenberg model. Okay, so this turns out to be generically true for all groups. It turns also to be true for these more general categorical symmetries. So this is something that we proved very recently. Okay, so there's a completely general way of understanding and of characterizing all operators that are symmetric with respect to these more general symmetries. Okay, so it turns out that all these kind of cases that are now like relief, split chains, all these kind, they're all special cases of it. So this is basically all of this is it fits in that framework. Okay, so they all have these NPO, called as NPO symmetries. Okay, so why is this so interesting for us? Because if you could have a Hamiltonian that is written down in terms of somehow such Gaussian coefficients, and you try to understand what is the spectrum, or how can I understand somehow the eigenfunctions or the eigenvalues of that Hamiltonian. The only thing that is relevant of that Hamiltonian, because it's written in terms of Gaussian coefficients, is basically the structured factors of the algebra of Gaussian coefficients. Okay? Because to understand eigenvalues of Hamiltonian, you only have to know how do these different terms in my Hamiltonian multiply with each other. Okay, the explicit representation is not important. If you have two different realizations of that Hamiltonian in such a way that these HI kind of have the same structured factors, then you will have the same eigenvalues. The degeneracies could be different, but somehow the eigenvalues will be the same. And this is exactly somehow, of course, the key in understanding dualities. Because it will turn out that two Hamiltonians will be dual to each other if somehow they give you different realizations of somehow something that is a sum of local terms, and these local terms have the same structure factors. If you multiply them by each other, you will get the same values. Okay, and indeed, somehow, this of course has to do with the fact that if you multiply two of these Gaussians, they're related to each other by these 6J symbols. These 6J symbols. Now, these are these 4 F symbols. So if you can go back to here, so all of this, they were like all this whole zoo of F symbols. But somehow only the F symbols of the category D are completely responsible for the algebra of your local operators. Nothing else. It's completely irrelevant what M is. It's completely irrelevant what C is. To determine the spectrum of a Hamiltonian using this Wigner-Eckert theorem kind of ideas, the only thing you need to know is basically these 4 F symbols. So in particular, it means that given such a category D, possible choices of M will give you Hamiltonians with exactly the same spectrum as the original one. Okay? They will have different energy, because if you can't change M, then it turns out if you fix D and M, this completely fixes C. They will have completely different symmetries, everything else, but nevertheless, they will have somehow exactly the same spectrum. It turns out that all known dualities, okay, including Jordan Wigner, Krams, Vanek, and Tasaki. These are somehow they are exactly of this form. So for us, this is again somehow the negative influence of Tasaki is coming up there. So this kind of Tasaki transformation was a key and to develop this whole further framework. So what Professor Tasaki realized is that if you kind of take this spin one Heisenberg model and you actually do a transformation, that instead of having a STT phase, you actually go to a completely symmetry broken phase. Okay, and this Kennedy-Tasaki transformation is a duality transformation that is exactly of this kind. Okay, so it's actually related from these F symbols by basically choosing the same D. The category D is just Z2 times Z2, and somehow the category N is two different ways in which you kind of choose somehow your module. There's two different choices of your module that you can make, and these two different choices of module will give rise to kind of two different realizations of somehow the same Hamiltonian, and these two Hamiltonians have the same symmetries, but of course they are very different. One is actually an SVT phase, the other one is completely symmetry broken. So there's no that actually these intertwines, like all these transformations like Jordan Wigner and all this, they, of course, generalizing this to arbitrary symmetries and categorical symmetries and non-abelian symmetries, they have explicit NPO forms again. So you can write this down as an explicit NPO, and with the Hamiltonian on one side, you can pull it through this intertwine and get the NPO, this dual to it. Okay, so but I'm seeing I'm going way too slow. So how much time do I have left actually?
1 minute.
Okay.
But we don't have anything after this.
I will try to speed up. I have to apologize that I'm too slow, but I've got many questions, so that is a good.
Yeah.
Okay, so anyways, all of this actually led to somehow something that I'm very excited about. Okay, something that actually this whole framework of understanding symmetries and indeed the symmetries in many body systems kind of is kind of leading to a completely new way of looking at somehow these different phases of matter. So remember that we were interested in somehow these phase diagrams. And what we have seen now is that actually this phase diagram, well, this was the phase diagram for one particular realization of somehow the symmetry, but I have all these dual realizations. I have all these dual realizations, and indeed these dualities is well known that, for example, Kennedy-Tasaki, if you take somehow your Heisenberg system, once you do the Kennedy-Tasaki transformation, you cannot go to a phase where somehow it's just a normal symmetry broken phase. There's nothing what you do to it. So the question is now, as you somehow, is there always a dual Hamiltonian where somehow all the symmetries are broken? This is, so given this phase diagram, is in every one of these phases, is there like a family of dual Hamiltonians where somehow all the symmetries are broken, and for which there is no degeneracy in the entanglement spectra. And this is especially interesting from the point of view of tensor network simulation and DMRG, because actually if you do tensor network simulation, and that's, I didn't talk about this at all, but this is the real reason that people are interested in tensor networks, is that they allow you to simulate many body systems. The cost of it is very much dependent on how the entanglement structure looks like. And the less entanglement you have, the more efficient these algorithms are. Okay, so if somehow in every one of these phases you can go to one where all the Schmidt coefficients somehow has just a single degeneracy, then you have a much more efficient way of simulating these systems than the original ones. And indeed, this is exactly somehow what we realized. Using somehow this whole formalism now of bimodule categories, there's that for every one of these phases, there's kind of unique dual phase in which all symmetries are broken. Of course, the dual symmetries might actually not be just normal global symmetries like in the original model, they will actually be categorical. So even in this case of a normal A4 symmetry, it turns out that to have the most efficient representation of somehow these wave functions, you have to go to Hamiltonians with categorical symmetries as opposed to normal on-side symmetries. Okay, so there's that. So how the wave functions, if you kind of look at this dual Hamiltonian and you have no degeneracy here, to relate them to the original model, you have to indeed put this intertwine. So you have this wave function. Multiply this wave function with this NPO intertwine, and that maps to one theory to one. And this is exactly the object that introduces all the degeneracies in the spectrum. Okay, so while we did this, again, if you can do this, the generality, I would be very glad to explain this whole diagrams. These are all commutative diagrams to people that are interested. But let's just kind of look at the numerics now, because you can use this for numerics. Have indeed somehow this representation. Again, for A4, there turns out to be exactly 7 modules. Okay, there's 7 choices of M for this given D. So there's kind of 1, 2, 3, 4, 5, 6, 7. This is actually these two are the same, some kind of rescaling being done to show that actually this is indeed effectively a degeneracy. But anyway, these are the 7 possible modules to deal with this. And indeed, if you can look at the entanglement spectrum, somehow it's immediately clear that for the SBT phase, this is the one that somehow this is the one that you need. And indeed, if you can look at the amount of memory you need to store that wave function using this module, it's much less than somehow using all the other modules. This is because this is basically what your wave function is. If you write it down in this representation, this would exactly do the Kennedy-Tazaki transformation. Of course, there's an A4 kind of related one, but it's very similar to what happens there. And this is the one that destroys also the degeneracies in your. Yes.
Yeah. So does it mean that this duality, which is MPO, so it does mean that this duality of the which is essentially MPO, the stores all the entanglement.
Exactly.
And
Exactly.
yeah, then you go to the kind of the dual
exactly.
state.
So here you break all the symmetries, and this MPO on top of it then kind of puts these degeneracies. Because this is clearly something with a non-trivial bond image.
Right. Okay, I see. So so you basically transfer the kind of the entanglement in the original state to the MPO.
Exactly. And this is universal. This is something that is the same for a phase, and that means that's why you have such a huge compression in information.
Okay. Yeah.
So okay, we did the same like the 4 symmetric phase. You can immediately see, okay, this is the one that is relevant. This is the one that for which the Schmidt coefficients go down the fastest, or for which you need the least amount of information, and so further. So anyway, what we were able to prove using this, especially using my somehow postdocs Lawrence Lotens and Clément Delcamp, who's now professor in IHES in Paris. So for every Hamiltonian, there's a unique dual one with the same spectrum, but which is completely symmetry breaking with respect to its dual symmetry. Okay, so this is already from the point of view of the conceptual point of view, this is very interesting. This is really somehow the one that well, this turns out that somehow you can predict already what this symmetry will be. This dual has it actually is related to the structure of your excitations in the original theory. This is something universal. But anyway, so the entanglements, the degeneracies in the entanglement spectrum are completely kind of obtained then by kind of restoring, kind of intertwining this back to the original theory. And indeed, somehow the degeneracies can always be removed by going to the optimal dual theory. Okay, so this is exactly somehow, this is basically a new way of understanding exactly what we're. Okay, so of course, somehow what is especially exciting is that this work provides a bridge between extremely abstract mathematics and something very tangible, namely something that you can use in doing mathematics. Okay? Because actually it turns out that it gives you lots and lots of mileage. It kind of allows you to simulate many body systems in a much better way. And I think it turns out that if you kind of look at the way people have dealt with symmetric tensor networks, okay, there's a huge industry of people that actually make code using tensor networks and symmetries. Effectively, what they are doing can be understood in this language, but somehow what they have to do is always somehow, they call it recoupling. Okay, they have a Hamiltonian here, they push it through this intertwiner, they define it here, and then they have to go back. And in every step of their Hamiltonian, they have to continuously kind of recouple with 6J symbols, recoupling kind of operators to kind of relate things, and it's very costly and very expensive. What we say is, no, there's a much simpler way of dealing with this. Just go to the dual Hamiltonian and do everything here, and after you simulate the whole thing, go back to the original.
So if you write the Hamiltonian in the MPO description, like the original Hamiltonian, what you're saying is that like you have to kind of go the dual Hamiltonian, whose the ground state is a simple entanglement structure. But like if you have a MPO Hamiltonian multiply this MPO like dualization, then the MPO description of the Hamiltonian becomes more expensive, right?
No, that's not true. The Hamiltonian, this dual Hamiltonian is exactly the same kind. Okay, so this is something that yeah, here. The only thing that happens is that in this dual Hamiltonian, these lines have different meanings, but they're exactly the same things. They're the same object, but they're just these blue lines have different dimensions. They're still local. Just local. So what's interesting, I didn't say it's indeed that any local symmetric operator in one theory is mapped to a local symmetric operator in the other theory with a different symmetry, but a local non-symmetric operator is always mapped to something non-local. Right. This is exactly the string order parameters. This is why you have like these string order parameters in these somehow theories. Like this is the origin of somehow the string order parameter in the AGLT. Okay, so because there's some kind of, you're going to go to this theory where all the symmetries are broken, you want to understand how do my order parameters in this theory, how can I describe them in my original theory? You have to pull them through this MPO. And this is exactly kind of generating the string.
In the case of say 2D toric code, like dual theory paramet. So in the case of 2D toric code, like a dual paramagnetic theory is the simplest, I guess, Hamiltonian and maybe but like now, like if you think about perturbed toric code, then the dual theory is kind of hard.
Okay, so actually the game that you have in 2 dimensions is even so we can repeat also. So I will stop my talk here because it's really tight. But so you can repeat also in 2 dimensions. Actually, instead of matrix product operators, these intervals become something that is called a BEPO, projected entanglement pair operator. So again, this is the representation theory of 2 categories. Okay, so 2 categories is something that even mathematicians are only starting to understand now, but the representation theory is actually something that we already worked with a long time ago, because this is the generalization of these MPOs to the 2-dimensional version. These are somehow, you can repeat exactly the same story, and this is exactly the gauging kind of thing that happens. You would indeed take something like an Ising model, tensor magnetic field, gauge the Z2 symmetry, and you would end up with something that looks like the gauge theory, like the toric code. But actually what you want to do is to keep the matter. You don't want to disentangle the matter like people do. You want to really have a Z2 gauge theory with matter and fields. Now, if you start with a symmetric Ising model in 2D, going somehow to the dual theory, the dual symmetry is actually a one-form symmetry. Okay, so all the loops, any loop is a symmetry. It's a symmetry, it's not that you don't have to impose it. So it turns out that if you start with the symmetric phase and you go to the dual one, all the loop symmetries, all the one-form symmetries are broken. So you have an extensive amount of symmetry breaking in the dual theory, which is exactly what is needed to kind of turn this area allowed to something that's much smaller. Because really, it's not just one symmetry that is broken, you break an extensive amount of symmetries. And this is exactly this, and so that means that in 2 dimensions it's even much more interesting than in 1D, because somehow gaining a factor of 2 or 3 or 4 in 1 dimension in 2D is a huge deal. So it's the difference between being able to solve, let's say, the Hubbard model and not. Okay, but I think I really have to stop here. I have many more slides. Stop. Thank you.
Yeah, thank you. No, thank you, Frank, for impressive talk. And I finally learned what we were doing. I really think so. So, any questions, comments? Yeah, of course, Misaki.
This question is within your instructions in the order of scalarity, duality, works for constant symmetry or time reverse, especially when the comment on that from MPO perspective.
This is exactly the question I wanted to ask you. This afternoon, actually, this indeed it's so in some sense what so maybe for if you look at what these dualities are, actually this is actually very much also based on work by a person here, Tashikawa, in the institute here. So he kind of classified all possible ways in which you can gauge a symmetry. And it turns out that this gauging the symmetries is exactly equivalent to somehow this module categories. Okay, so for the category is a group, then all the possible ways in which you can gauge is equivalent to choosing all possible modules. Okay, and it's not clear at all how you gauge time reversal or how you gauge something like reflection. It might be possible, and indeed, certainly from the point of view of SPT phase, it's very clear how to look at the entanglement degrees of freedom of something like the AKLT state or the spin on Heisenberg from the point of view of this time reversal. But what it needs to gauge this is not clear.
Thanks.
Any other questions?
Thanks on the last talk. So, I want to ask you about the point that you want to make is that instead of working with the original Hamiltonian, you like to work with the dual Hamiltonian with with a state with less entanglement, which is of course much better to be dealt with. But in the meantime, if you do the duality, you lose some information, right? You need to take care of the topological sectors. Like, so for example, if I'm interested.
No, okay, so indeed, so I was not careful. We solved this completely. So So it turns out that to do these dualities, of course, to do it carefully, you have to be very careful with boundary conditions.
Yeah.
And actually, it turns out that we completely wrote a whole paper on how to do boundary conditions with these dualities, and it turns out that actually the possible boundary conditions compatible with this whole framework, they are kind of completely labeled by all possible tube algebras. Okay, so this is not like an OPM tube algebra, that emerges very naturally here, and this is all it also kind of labels the topological sectors that you have in string mass. Okay, this is exactly the same object that forms the boundary. And if you take this into account, then you can actually see that all these dualities are unitary on the subspace that you're interested in, or subspace. Indeed, somehow by intertwining this, you completely understand how charge sectors and boundary conditions are then exchanged. Okay, so these are the kind of things. So this is completely under control. And what you have to do to make this dualities unitary is actually lift these boundary somehow the way. What is my boundary? So this is kind of a label. You kind of lift this to an actual quantum degree of freedom. You act on it with some hard circuit, then this whole circuit becomes unitary.
Okay, I see. Okay, thanks.
So this question from other mathematician. So first you talked about the example that before, and then there are seven different modules. I think. So and that what is meant is that probably it's a module category is semi-simple, so it's decomposed into that. And so that's an interesting subclass of the fusion category, but it's not true to. People try to extend to non-semi-simple cases. So most of the structures, F-simple, everything is the same, but it just doesn't decompose. And the question is, what is so that's a natural next case.
Exactly, I completely agree, and this is something that so for the moment we only looked at invertible binomial categories, but there's an exception. Actually, so we wrote a paper 2 years ago in which we extended this to Lie group symmetries. Right. So actually, it is possible to find NPO representations of SU2, and it turns out that the local tensors that we need for this, although the global NPO is a representation of SU2, is composed out of SU2 level Q tensors. So there's really a very natural connection between the group SU2 and actually the quantum group SU2 Q. Okay, and this in this case we could only do it if we had single non-like then it could not be simple. We have to be kind of we get the generacies there, and it seems that the only way we could do it is this. We are still struggling to understand indeed the exact mathematical kind of reasons why this is what seems to be important. That's even in that case, it's so what is crucial somehow to get this whole thing to work is that the fact that it's invertible actually related to the fact that indeed if I will point to this that both somehow this forms of fusion category and this forms of fusion category, and that indeed this is basically these labels or the blocks they label the simple objects in their category. And if you're in semi-simple, then there's some kind of extra indices there that we have not been able to exactly deal with. But I would love to talk about this. Yes, it's a very good question indeed. So this is again one of these things. So the Lie group versions of a category theory, mathematicians would say, oh, this doesn't exist because the category theory should have fusion category should have finite number of objects. But it just works. I guess so if we do this for SU2, it just works and can use it.
I have a question. Just suppose that nobody finds string order parameter, nobody finds KT transformation, but somebody did this computation of entanglement and spectrum and found this double degeneracy. And suppose that you have this general theory, then is it kind of easy to come up with KT transformation?
No, this is completely general. This is to me an algorithm. It's just a black box. You have a certain category, you solve for the S symbols. If there's an algorithm for finding all the possible modules, and then there's some kind of a functor that tells you how to relate all these things. So all these things are completely automatic. You don't have to.
Automatic.
It's completely automatic.
Demystified, finally.
Yeah. Yes.
Okay. Yeah, that's fantastic. Any other questions or comments? Okay, if not, let's start.